Tangent to a circle. In this module, we will discuss about tangent to a circle. You have studied circle, radius and its center and various terms related to a circle like chord, segment, sector, arc, etc. Let us now examine the different situations that can arise when a circle and a line are given in a plane. So let us consider a circle and a line PQ. There can be three possibilities. Case 1. The line PQ and the circle have no common point. In this case, PQ is called a non-intersecting line with respect to the circle. In case 2, there are two common points A and B that the line PQ and the circle have. In this case, we call the line PQ a secant of the circle. In case 3, there is only one point A which is common to the line PQ and the circle. In this case, the line is called a tangent to the circle. We can define a tangent to a circle as a line that intersects the circle at only one point. Theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. We are given a circle with center O and a tangent xy to the circle at a point P. To prove that OP is perpendicular to xy, let us start the proof. We need to take a point Q on xy other than P and join OQ. The point Q must lie outside the circle. Note that if Q lies inside the circle, xy will become a secant and not a tangent to the circle. Therefore, OQ is longer than the radius OP of the circle. That is, OQ is greater than OP. Since this happens for every point on the line xy except the point P, OP is the shortest of all the distances of the point O to the points of xy. So OP is perpendicular to xy. Because the shortest distance from a point to a line is the perpendicular from that point to the line. From this theorem, we can also conclude that at any point on a circle, there can be one and only one tangent. Because there can be only one perpendicular from a point to a line. The line containing the radius through the point of contact is also sometimes called the normal to the circle at the point. In this module, we will discuss number of tangents from a point on a circle. As we already know now that from any point on a circle, there can be one and only one tangent. Now let us know about the number of tangents from a point inside a circle. So let us draw a circle on a paper and take a point P inside it. Can we draw a tangent to the circle through this point? Let us see. We observe that all the lines through this point intersect the circle in 2 points. so it is not possible to draw any tangent to a circle through a point inside it. Next, take a point P on the circle and draw tangents through this point. We have already observed that there is only one tangent to the circle at such a point. Now we are left with only one condition. Let us see that also. Now we will take a point outside the circle and try to draw tangents to the circle from this point. Observe the figure. We can observe that we can draw exactly two tangents to the circle through a point outside the circle. Here, T1 and T2 are the points of contact of the tangents PT1 and PT2 respectively. The length of the segment of the tangent from the external point P and the point of contact with the circle is called the length of the tangent from the point P to the circle. PT1 and PT2 are the lengths of the tangents from P to the circle. The lengths PT1 and PT2 have a common property. Let us see in this theorem. Theorem. The lengths of tangents drawn from an external point to the circle are equal. We are given a circle with a center O, a point P lying outside the circle, and two tangents PQ, PR on the circle from P. We have to prove that PQ is equal to PR. Let us start the proof. For this, we join OP, OQ and OR. Then, angle OQP and angle ORP are right angles because these are angles between the radii and tangents. Now, in right triangles OQP and ORP, OQ is equal to OR, radii of the same circle, OP is equal to OP, common. Therefore, triangle OQP is congruent to triangle ORP by RHS. This gives PQ is equal to PR by CPCT. Also note that angle OPQ is equal to angle OPR by CPCT. Therefore, we can conclude that OP is the angle bisector of angle QPR. That is, the center lies on the bisector of the angle between the two tangents. We will do some examples now. Let us take an example. Prove that in two concentric circles, the chord of the larger circle, which touches the smaller circle, is bisected at the point of contact. Solution. We are given two concentric circles, C1 and C2, with center O and a chord AB of the larger circle C1, which touches the smaller circle C2 at the point P. We need to prove that AP is equal to BP. Let us join OP. Then, AB is the tangent to C2 at P and OP is its radius. Therefore, OP is perpendicular to AB. Now, AB is a chord of the circle C1 and OP is perpendicular to AB. Therefore, OP is the bisector of chord AB, as the perpendicular from the center bisects the chord, that is, AP is equal to BP. Next example is, two tangents TP and TQ are drawn to a circle with center O from an external point T. Prove that angle PTQ is equal to twice angle OPQ. Solution. We are given a circle with center O, an external point T, and two tangents TP and TQ to the circle, where P, Q are the points of contact. We need to prove that angle PTQ is equal to twice angle OPQ. Let angle PTQ is equal to phi. Now, TP is equal to TQ, as the lengths of tangents drawn from an external point to a circle are equal. So TPQ is an isosceles triangle. Therefore, angle TPQ is equal to angle TQP is equal to half into 180 degrees minus phi is equal to 90 degrees minus half phi. Also, angle OPT is equal to 90 degrees by the statement that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So, angle OPQ is equal to angle OPT minus angle TPQ is equal to 90 degrees minus 90 degrees minus half phi is equal to half phi is equal to half angle PTQ. This gives angle PTQ is equal to twice angle OPQ.
Properties of tangents, Part 1. Let's take an example. If OA and OB are radii and PA and PB are tangents to the circle, assign a special name to quadrilateral OAPB and justify your answer. Let's solve this. OA is equal to OB as radii of a circle are equal. PA is equal to PB as tangents to a circle from an external point are equal. Therefore, OAPB is a kite. Let's take the next example. Triangle ABC is right angled at B. A circle with center O has been inscribed in the triangle. If EB is equal to 15 cm and BC is equal to 8 cm, find the radius of the circle. Let's solve this. Using Pythagoras theorem, we get AC is equal to under root of AB square plus BC square is equal to under root of 225 plus 64 cm is equal to under root of 289 cm is equal to 17 cm. We draw OP perpendicular to AB, OQ perpendicular to BC and OR perpendicular to EC. Therefore, OP is equal to OQ is equal to OR is equal to R, where R is the radius of the circle. PBQO is a square. Therefore, PB is equal to BQ is equal to R. Therefore, AP is equal to 15 cm minus R and QC is equal to 8 cm minus R. Now, tangents drawn to a circle from an external point are equal. Therefore, AR is equal to AP is equal to 15 cm minus R, and RC is equal to QC is equal to 8 cm minus R. But AR plus RC is equal to AC. This implies 15 cm minus R plus 8 cm minus R is equal to 17 cm. This implies 23 cm minus 2R is equal to 17 cm. This implies 2R is equal to 23 cm minus 17 cm. This implies 2R is equal to 6 cm. This implies R is equal to 3 cm. Let's take the next example. In the figure, PQRS is a cyclic quadrilateral and the tangent to the circle at P is the line AB. If angle RPB is to angle RPA is equal to 2:1 and PS bisects the angle RPA while PQ bisects angle RPB, then find the measures of the angles of the cyclic quadrilateral. Also prove that SQ is the diameter of the circle. Let's solve this. Angle RPB plus angle RPA is equal to 180 degrees and angle RPB is to angle RPA is equal to 2:1. Therefore, angle RPB is equal to 2 into 3 into 180 degrees is equal to 120 degrees and angle RPA is equal to 1 by 3 into 180 degrees is equal to 60 degrees. As PS bisects angle RPA, angle SPA is equal to angle RPS is equal to half into 60 degrees is equal to 30 degrees. As PQ bisects angle RPB, angle BPQ is equal to angle RPQ is equal to half into 120 degrees is equal to 60 degrees. Now, angle RPB is equal to angle PSR is equal to 120 degrees because angle between tangent and chord is equal to the angle in alternate segment. Therefore, angle RQP is equal to 180 degrees minus angle PSR is equal to 180 degrees minus 120 degrees is equal to 60 degrees because opposite angles of a cyclic quadrilateral are supplementary. Again, angle SPQ is equal to SPR plus angle RPQ is equal to 30 degrees plus 60 degrees is equal to 90 degrees. Therefore, angle QRS is equal to 180 degrees minus angle SPQ is equal to 180 degrees minus 90 degrees is equal to 90 degrees. We can see that the chord SQ subtends the right angle at P. Therefore, SQ is the diameter of the circle as the angle in a semicircle is a right angle. Properties of tangents, Part 2. Let's take the next example. A, B and C are 3 points on a circle. The tangent at C meets BA produced at T. Given that angle ATC is equal to 36 degrees and angle ACT is equal to 48 degrees, calculate the angle subtended by AB at the center of the circle. Let's solve this. Join B to C. Let O be the center of the circle. Join O to A and B. In triangle BCT and triangle ACT, angle BTC is equal to angle ATC is equal to 36 degrees, common angle. Angle ACT is equal to angle TBC is equal to 48 degrees. As angle between tangent and chord is equal to the angle in the alternate segment. Therefore, remaining angle CAT is equal to angle BCT is equal to 180 degrees minus 48 degrees plus 36 degrees is equal to 96 degrees. Now, angle BCA is equal to angle BCT minus angle ACT is equal to 96 degrees minus 48 degrees is equal to 48 degrees. Therefore, angle BOA is equal to twice angle BCA is equal to twice into 48 degrees is equal to 96 degrees. Because angle at center is equal to twice into angle at the circumference. Let's take the next example. ABC is an isosceles triangle in which AB is equal to AC. If D is the midpoint of AC, prove that AB is equal to 4AP. Let's solve this. Let AB is equal to AC is equal to 2x. Then AD is equal to half AC is equal to x. AB is a secant and AD is a tangent. Therefore, AP into AB is equal to AD square. Product of segments of secant is equal to square of tangent. Therefore, AP into 2x is equal to x square. This implies AP is equal to x by 2. Therefore, AB is equal to 2x is equal to 4 into x by 2 is equal to 4AP. Let's take an example. Two circles with centers O and P and radii 8 cm and 4 cm touch each other externally. Find the length of their common tangent QR. Let's solve this. Join O to P and Q. Join P to R. Draw SP perpendicular to OQ. Now SP is equal to QR as they are opposite sides of rectangle PRQS. OP is equal to 8 cm plus 4 cm is equal to 12 cm. OS is equal to 8 cm minus 4 cm is equal to 4 cm. Therefore, SP is equal to under root OP square minus OS square is equal to under root 12 square minus 4 square centimeter is equal to 8 root 2 centimeter. Therefore, QR is equal to 8 root 2 centimeter.